All right, so we'll talk a little bit more computational geometry today. I found some source code online that does a oriented bounding box class. Normally I use axis-aligned bounding boxes because they're fast and simple and easy. So if you want to know if a point is inside of a axis-aligned bounding box, all you got to do is do basically this right here. You just basically say, is the point, this is what I'm doing with my CSI 40 people, like it's very basic. Add a new page, 10, 19, 21. Tablet dead? There we go. So if you've got a box, you've got like a minimum x and a minimum y, right? And you got a maximum x and a maximum y. And so if you have a point and you want to see if that point is inside of the box, you just basically say, is p dot x, in between x1 and x2, and is p dot y in between y1 and y2. You guys understand? Like, it's pretty easy. It's just a four-part if statement. Yeah? Okay. So an oriented bounding box looks like this. It could be at an angle or whatever, and then you want to know if that point is inside of there. You can't just use the x and the y because the y-axis had a weird angle. Right, because you have your x-axis and your y-axis, right? And when you have a bounding box with axis aligned, it's very simple. So what you have to do, if you have an axis aligned bounding box, and this is more of a bounding trapezoid or something, I don't know. What you do is you basically, this thing has a rotation matrix, right? So what you do is you just rotate it to be axis aligned. And this is what I actually did in my game engine. So what you do is you simply rotate it. So if this guy has been rotated like counterclockwise, I don't know, like 50 degrees or something, then you just rotate it and you rotate the point 50 degrees to the right, and then you can do an axis aligned bounding box check, right? And that would be outside. Right? So in order to do code like that, though, you typically have some sort of math library that does the rotations and the scaling and the translations and the bounds checking and stuff like that. So this one here, it's got a bounding box. It's got a function called isPointInBox. It takes in a point, and basically it's just rotating the point with the box's rotation, and then it just does the if statement here, and it's doing so. Oh, I see. So it moves the box so that this is at 0, 0. Okay. So it not only rotates the box, but it translates it so that it is at 0, 0. So all you have to do is see if a point is within the thing. You just have to check against the size in the x, the y, and the z directions. And or maybe, no. Maybe the center is actually, maybe the center is here. Maybe it makes that the center. And then the extent is going to be the extent of x and the extent of y. And so you just take the point and they're absolute valuing it and see if it's smaller than either all three of the x, the y, and the z extents. So that's how they're doing it. There's different ways you can handle boxes. It looks like they're doing it by having the width, the height, and the depth held, rather than the min and the max points, which is a certainly valid way of doing it as well. But it cuts down on the number of checks. So rather than 6 checks, they have 3 checks. So if statements can be expensive, and so there's probably a speed reason for doing that. Do you guys see that? So rather than having to check between the minimum, the maximum, the minimum, and the maximum, what they do is they move the center of the box to here, and then they have the width, the half width of the box, and the half height of the box. And then they absolute value the point, which is a very simple calculation. And then if that point is smaller than, if its x value is smaller than the x extent, and its y value is smaller than the y extent, and its z value is smaller than the z extent, then it's within the box. So, That's far easier than how you thought to do it. Yeah. I sat there and really scratched my head on that one when I was building my game engine. And I was fresh out of high school, right? And I didn't know linear algebra yet. And so when I started there, they handed me a book on essentially linear algebra, and they're like, learn this. I worked there for a week, and probably helped the company land a contract. I was about to go on a trip to Puerto Vallarta, because I had signed up for my senior trip prior to getting hired at this company. They're like, no, come in for a week and work for us. And it turned out to be a great week because they needed this bug fixed. The Admiral was coming in, and it's like Friday, and I'm like flying out to Puerto Vallarta at like 8 p.m. or something. And my dad's there because I didn't even have a driver's license yet. This is right before I got my driver's license. My dad's like hovering there, and the company boss is sitting there like, can Bill stay a little bit longer? You know, and I'm like frantically debugging their code because the Admiral's coming in. They're going to do a demo and sell off these like $100,000 headsets to them, and the code wasn't working. And so I used my debug skills, and it was like 5:30 in the afternoon. I'm leaving to Puerto Vallarta, and I find the bug, get it fixed. Yeah. I don't know if I've told you this, but one of the bugs that I had to fix was that they glued a screen in upside down. So we had this very expensive headset. It was a VR headset, and it was made of multiple screens glued together because they didn't make large LCD screens back in those days. They were all small. And so they had this coating that would like allow the LCDs to glue together without a visible seam. It was quite brilliant. And the engineers who had put it together had glued two of the screens in upside down. And so I was like frantically, me not knowing linear algebra, trying to figure out how do I rotate the screen on screens 2 and 9, you know? And Walker, have I told you the story before? About the upside down viewport. And fortunately, somewhere within the code, there was a separate view matrix for each of the different viewports. And all I had to do was go in there and hard code it to rotate it 90 or 180 degrees for number 2 and number 9. Fired up the thing worked, and then I left for vacation. And on vacation, they gave me a book of linear algebra, and so it helped with this kind of stuff. But yeah, the solution I came up with for this kind of thing was if you have, and one of the reasons why I like spheres is because it doesn't matter how you rotate a sphere, right? It's always the same. But for my bounding box checks, what I did was if I had a rotation on it, then you just sort of unrotate it, and then the thing that you're trying to test, you rotate it the same way, same matrix, and then you do the thing as if it's axis aligned. It's quite easy. Okay. So basically they're inverting the matrix. So if it's been rotated 45 degrees, this will unrotate it 45 degrees. If it's been translated 10 to the east, it'll go 10 to the west. And so it will basically undo, you know, the thing, and the point that you're passing in gets carried along for the ride. So it gets rotated 45 degrees backwards as well. It's quite simple. So if this return true, yeah, they probably could simplify this down even further. This could be simplified to just that. No if statement. Simple. Okay. Yep. Yep. Simple. Okay. Check if sphere overlaps into part of the bounding box. Okay, so this is sphere versus box, and it's doing the same thing. It's inverting the rotation of it so that it becomes an axis-aligned box. And then what it's going to do is go through the extents of the box, the x, the y, and the z, and see if P, what is P? That is the center point. So if the center point is further away than any of the extents, then it has to compute the distance from the center point to that extent. So go back over here. getting kind of nostalgic for this because I did this back in the day. So they have a box that is at 0, 0 because they've inverted the operation. And so they have an x extent and a y extent, and then they got a sphere. So if the sphere is on the inside, then you're good to go. It overlaps, right? But if it's on the outside, then what you do is you see, because you got a radius of a sphere, right? And so basically, that point here is always going to be the closest to the box. So you just take the radius and radius the distance to it, and absolute value of the center point minus the extent, and that's, is it? Yeah, it's absolute valued. Okay. Yeah. So they don't have to check in all directions. They just have to check in 2 directions or 3 directions. It's three-dimensional. So the absolute value of the distance. So this is the distance from the sphere to the edge. Okay. On the x coordinate plane. So this is the center point x. So they basically take the distance between these two, and then they square the distance, and they see if the distance squared is smaller than the radius squared. And if it is, if the distance squared is smaller than the radius squared, so the distance to here is smaller than the, if that distance squared is smaller than the radius squared, then it's touching. And they do that for, and they add them all together. Okay. So they add it together for the x, the y, and the z directions to see if it's touching. Take center point of both circles, make sure the distance, the 2 circle collision is simple. That's one of the reasons why I like doing circular collision, at least for simple tests, because it's real easy. Yeah, good point, Walker. So if you've got a radius here, and then you got so this is a 0.1, this is a 0.2, and you got a radius here. It's a terrible sphere. Circle. All you have to do is see if the distance between the two is smaller than the sum of the radiuses. Very easy. Very easy to check. I'm going to redraw that circle. Okay. Betancourt, does that make sense? So you just take you do the Pythagorean distance between P1 and P2. So if the square root of, P1 dot x minus P2, I don't want to write this. If the distance between the 2 points is like 10, and the radiuses are both 3, then they don't touch. If the distance is 10, the radiuses are both 20, then they touch. Because you just add the radiuses together, because the nearest point is this way. So you just add R1 plus R2 and see if that's smaller than the distance. Okay. Box outside plane. If it's behind a plane, oh, that's cool. So they have a plane defined probably as a normal vector and a point. Yeah, okay. So algebra, geometry, whoever thought it'd be useful. So let's say we've got a plane. We got a normal vector. The normal vector always points out of the plane, and then we have a point somewhere on the plane. Doesn't matter where, because it's has an infinite extent, right? So we want to know, is this box we have on one side of the plane or the other, or if it's split? This is actually a very important test to do, because when you're doing like binary search partitions, binary space partitions, or various BDH type things, it's good to know, is it on one side? You can construct a series of division planes through the world and say, okay, everything's on one side or everything's on the other. Make it easy to find. So they invert the normal. So what they do is they invert the normal. So the normal is just pointing in one direction. I don't know which. It's considered forward, but we'll say X is forward. And then the box comes along for the ride like that. And then they turn the normal. Let's see. Okay, so they absolute value the normal. Okay. So if it's going to be pointing in the positive direction, X, Y, and Z. And then, or maybe they're rotating it based on the, maybe they're rotating it based on the box. Invert simple. Yeah, so they're rotating the normal based on the box. Okay, so the box is going to be axis aligned. And then they do a dot product between the normal and the extents, and the distance from the center of the box to the plane. And then that's it. Is a line in a box? Isn't it? Does it intersect? Okay, yeah, that makes more sense. And so this is kind of a fun one to do. And again, if you want it to be an oriented bounding box, all you have to do is just do the inverse of the rotation, and you'll get it. So why don't we do this one? This will be fun. Is box in a box? Yeah, I don't want to write that one. That's crazy. If any part of a box inside of it, any part of the box, yeah. That's a lot of code. I'm sure it's fast, but there's simpler ways you can do that. At least as far as writing code goes. Okay, so let's do line box intersection. Have we done this one yet? So like, let's say we've got a rectangle, and then we've got a line. We've got a line, we got a box, a beat box, an axis aligned bounding box. Okay? And we want to return true or false. Does this hit? You guys want to, have we done this before? Nope. Dawn, do you remember doing this before? Because I don't remember doing it before. I did it with Walker. I don't think I've done it with you guys. Is cursed because Kearney's not using Vim right now? Technically, I have Vim mode on Visual Studio. Kind of like everything I use has Vim mode on it. Okay, so let's do this on this server. So the do you guys remember how to do line intersection from algebra? How do you determine if two lines are touching? Might be good to review. Well, the good news is we actually don't even need to use the full equation for that, because this is a axis aligned bounding box. It's vertical. So let's say that our bounding box, let's do the same trick they did, and let's just always have our bounding box be at 0, 0. Okay? What is this point called in algebra? It's the y-intercept, yeah. And so all you have to do is say, is the y-intercept of this line between the maximum and the minimum value of y? You see that? And then what about the z-intercept? Okay. And then what about when y is equal to, I don't know, whatever number this is. Let's say it's 5. What's the y equals 5? You know, what is the x equals 5? Yeah. Right? So there's actually 4 points that we can test for. We can test for when x is minimum, x is maximum, x is minimum, x is maximum, y is minimum, y is maximum. And all we basically need to do is say, does the line cross between the min and the max of those points? So if we have, let's say this is, do you guys remember mx plus b? That's the equation for a line. So let's say the slope on the line is, this looks like 1, and the y-intercept is 3. So if our equation is y is equal to x plus 3. What is the y-intercept? Bellin? Highly advanced algebra here. If y is equal to x plus 3, at what point does it cross the y-axis when x is equal to 0? If y is equal to x plus 3, what is y when x is 0? Are you driving right now? If you're driving, you don't have to answer. It's fine. When x is equal to 0, what is y? It's 3. That's it. And so all we have to do is check if y max is 5 and x max is 5. All we have to do is say is when x is 0, is y between 0 and 5. That's it. If it is, it hits. If it's not, then we have to check the other. We have to check 3 of them. I don't think we have to check 4. Because I don't think it's possible for the line to cross and not hit 2 of them. You know what I mean? I think you only need to check 3, really. Maybe if it's tangent or something. No. I don't think so. You only need to check 3 of them. Okay, so how do I check to see if it hit over here? When x is 5, what value is y over here? So we check to see if the line intersects the edges. Yeah, so the box is defined as like y min, which I guess if we're using their trick is going to be 0, x min 0. So the box is just defined in terms of x max and y max, which I'm saying is 5 and 5. So what you do is you take the equation for the line, which is y is equal to x plus 3. You plug in 0 for x, and you see if the y that you get is between the minimum and the maximum. If it is, you're done. Return true. If it's not, then you try x equal to 5. If x equal to 5, you get 8. Is 8 between 0 and 5? Okay. Yeah, it is 8. And then you do the same for y. So you try y is equal to 0. So 0 is equal to x plus 3. You get x is equal to negative 3. So negative 3 is over here. Negative 3 is not between 0 and 5, so that's a miss. So let's try y max. Y is 5. 5 is equal to x plus 3. X is equal to 2. So this is going to be at 2. 2 is between 0 and 5, so that's a hit also. So we got 2 hits. We got 1 hit when x is 0, and we got 1 hit when y is 5. And so that tells us where the bullet entered the box, and it tells us the point where the bullet left the box. Whichever one's closer to the gun. Let's say the gun's over here. The gun's over here. Then you can shoot a box, and you can penetrate through it, and have the bullet come out the other side and do another trace line. Okay? Or if you're doing like ray tracing, oftentimes these bounding boxes will be hierarchical. So they'll be nested inside of each other. And so they'll hit a bounding box, and then inside of the bounding box, there's other bounding boxes inside of it. And then you take this point of impact and you continue the line trace. And these acceleration structures can make finding the next box you hit log n time. And so this allows you to find, you can shoot a bullet and find out what you hit in order log n time. It's pretty fast. Okay, you guys want to see this in code? There's a lot of uses for this. And the oriented version of it where you could rotate these things just involves you inverting the rotation and then doing the same code. Is box and box. Oh, because these are oriented. Yeah. Yeah, and so these aren't. Yeah, if they're AABBs, it's a lot easier, I guess. Yeah. You're morbidly interested in how painful it is. It's not painful at all. So check it out. And this is really nice when you're making a video game, you know. a line trace is one of your primary tools, you know. And if you want it to go fast, then use AABBs. AABB, axis aligned bounding box. It's a very common acceleration structure to make, you know, you shoot. There's millions of objects in the world. You don't want to have to go through every object and see which one you hit. You want it held in some sort of data structure, and the data structure will very quickly tell you hit the tree over there. And you want to be able to find that in log in time. Log base 2 in time. Right. Okay, so let's do this. Vim main.cc. Okay. So, int please enter the slope. And we're not handling vertical shots because it's an integer. It's fine. Enter the slope. mx plus b. Please enter the y-intercept. And we will have the x extent and the y extent. And so I'm moving it so that the corner of the box is on 0, 0. And they had it, so 0, 0 was in the center of the, I'll just call it x, I'll call it x size. Please enter the width of the box. Please enter the height of the box. And the box is always box's bottom left corner is 0, 0. And if you don't do that, it just adds a couple extra lines of code. It's not a big deal. Okay, so you guys understand what we're doing here? We're getting the line, we're getting a line, and we're going to see if it hits a rectangle or not. Okay. The rectangle's bottom left corner is on 0, 0. Its right upper right corner is at x size, y size. Make sense? This corner here is at 0. This is at 0, 0. Okay. I call it x max and y max, just to have it match. Okay, so we want to return true or false, right? So let's make a function for it. Call it line box intersect. So we will pass in a int m, int b, int x max, int y max. I should probably be using doubles, huh? Yeah. Probably should. Okay. Okay. So now we just need to write the function. So there are 4 points that the bullet can hit. The left edge, top edge, the bottom edge, and the right edge. There. So we'll just try all 4 of these. So the left edge of the box is when x is equal to what? What is the left edge of the box? That's when x is equal to what value? Guys still here? When is the it's 0. It's when the left edge is 0, always, because we're defining as the bottom left corner as x0, y0. So the minimum x is always going to be 0 for this code. The minimum y is always going to be 0 for this code. And so we just need to do this mx plus b calculation. So when x equals 0, the right edge of the box is when x is equal to x max. The bottom edge of the box is when y is equal to 0. And the top edge of the box is when y is equal to y max. So all you have to do is substitute in for y. Remember the equation for algebra for a line is y is equal to mx plus b. So we just substitute in x equals 0 or something and see if the result is between 0 and y max. In this implementation, usually when I write this code, there's a y min and a y and an x. There's an x min and an x max, but I was inspired by that code that I just looked at for the first time, and I'm like, you just put it at 0. It makes life simple. Okay. So before we can do this, we would have to do the inverse translation. Okay. So it's substituting. So basically, we substitute in x is equal to 0, and then we see if the result is between 0 and y max. And then we try x equals x max. Is the result between y min and y max? Do the same for y equals 0. Do the same for y equals 5. Y equals 0, y equals 5. So we try substituting all 4 things in, and we can see which edges it hits and which ones it doesn't hit. If it doesn't hit all of them, then it's a miss. So, yeah, let's make all these things doubles. Otherwise, we'll get some really weird. Okay. We get some really weird aliasing effects. Okay, so the double, so the y-intercept is equal to what? It's when slope times 0 plus b. So if the y-intercept, if the y-intercept is greater than 0 and y-intercept, and we can allow equals as well, and the y-intercept is less than or equal to y max, so if it's between the minimum and the maximum here, then we got to hit. Return true. And we're not reporting back where we hit and what, the outgoing shot is. We're just returning the first time we get hit, we just return true. Okay, so yeah, okay. And then for the other y value, we try x max equals 5 or whatever. So the y-intercept here is equal to mx plus b, right? So it's going to be m times x max plus b. And then we just repeat the code here. And then we'll do the x-intercept. So the x-intercept is when y is equal to 0. So where does it cross the x-axis? Is when y equals 0, right? And so it's going to be back over here for this one. So the x-axis is when y equals 0. So when y equals 0, 0 is equal to x plus mx plus b. So So 0 is equal to mx plus b. So x is equal to negative b divided by m. Right? Negative b divided by m. Okay. So that's the answer there. So if our slope was 1 and our y-intercept was 3, then it intersects at -3. Slope's at 1. Right. So this is just equal to what I say, -b divided by m. So -1 times b divided by m, like that. I don't think we need a parentheses, but I'll slap one on anyway, just like that. And that is our x-intercept. So if the x-intercept is greater than 0 and the x-intercept is less than or equal to x max, return true. And then we do the same thing here, except now for this one, instead of 0, we're going to use y max. And so this is going to be y max, it's terrible handwriting, minus b divided by m. Minus b divided by n. And then we just do the same code here. So again, if it's within range, return true. Otherwise, return false. Slope of 1, y-intercept of 3, the width of the box is 5, height of the box is 5, hits the box true. Enter the slope, -1, it's going this way, y-intercept of -3, and it's a 5, 5 box, it misses. So that second line I gave you there was going down this way. Like, I know algebra is scary, but like, it's not too bad, I don't think. And all you do if you wanted to have the minimum and minimum x and y is rather than using 0, you would just use x min and y min. That's it. You just work that into here. That y is essentially 0 there. That's why it's -1b. It's y, it's 0. So you just put those values in instead of 0, and then it'll work with any rectangle. That's it. And so this test here, though, is actually really fundamental, because if you have bounding boxes inside of bounding boxes inside of bounding boxes, then you can throw a line out. Did it miss everything? Your bullet missed. If it hit a box, then you go to its two biggest children and see if the line hit either of those. If they both missed, you missed. If it hit one of them, then you go into that one's two children. You keep doing that further and further down until you get to a leaf node. A leaf node indicates something solid. Hit. Okay. Where? And return, and so this thing would normally not just return true or false, it would return all sorts of information about the point that was hit, but that's essentially what it is. And that's how RTX video cards work. They do this. So you generate a BVH. A BVH is a bounding volume hierarchy. It's just a bunch of rectangles inside of rectangles inside of rectangles. And then you throw a line. And the graphics card, your 3090 or what have you, will do that search for you. It does this in hardware. And it does it very quickly. And you can do not just one, but lots of them. You don't need this for like firing a bullet, because you know how many bullets a second do you fire? Like one, right? Maybe, or if you're firing 30 bullets a second, not a big deal. What they use this for with the RTX video cards is they'll send 10,000 light rays out through the screen, and they see the geometry that it hits. And so it's like a echolocation on a bat. You kind of shoot sound waves out and you listen to the reflections you get back. So you send a light ray out and it hits a chair. Okay, cool. So maybe you draw a point there on the screen, but more realistically, once you hit that chair, then you send another ray through the world trying to go to each of the light sources to see how much light is actually hitting that chair. And if it hits a mirror, then the light can bounce off of it. And so you end up getting this sort of cascading effect of like light rays bouncing around everywhere. And so if you want to have a really nice, accurate ray traced image, having a hardware acceleration is really nice on it. So I'll fire up the RTX showcase here, but that's really all it is. Like when you hear all about this, like RTX, 20 series, 30 series graphics cards, all it's doing is that quickly in large numbers in parallel. That's it. This requires the RTX Global Illumination plugin, which cannot be found. Requires a DLSS plugin. I guess I can't run you anymore, huh? Okay. Yeah, I'll just delete you then. Bye-bye. Yep. Can you see the code real quick? I'm typing, sure. So it's just 4 line intersection tests, and they're real easy to do because the lines we're testing them against are vertical or horizontal, and that's a really, really simple if statement to do. If you're doing a line versus the y-axis is something they literally teach in 7th grade algebra, right? Find the y-intercept. Okay, it's B. That's it. That's 7th grade algebra. Right? When x is 0, what's the y-intercept? B. Mx plus b. And then you just see if that y-intercept is between 0 and the maximum value. If it is, you got to hit. It's easy. And technically, you don't need to do all 4 of these. And the reason why you don't need to do all 4 is because any line that hits the box is going to hit either on 0 or 2 faces. You don't actually need to do all 4 because if it hits one of them, it'll come out the other side. But yeah, I just did it for the sake of completeness. Okay. So that is it for today. No homework for today. Just if you have any missing homework, just turn that in by Thursday. Okay. We'll probably do some simple coding or something, but I know a lot of you have some missing homework assignments and things like that. Just work on those and turn them in. That's funny. Input. That is really funny. Yeah, it's fine. I'm not a real big stickler for deadlines in this class. It's game development. It's not computer science. So work on your levels. If you haven't done them. 33% of the class today is missing assignments. Yeah, or whatever. So not a big deal. Just work on those. I'm not going to give you anything new. Let's catch up. Yeah, I know 26 has been tough. So okay, that's it for today, guys. I'll see you on Thursday.